Time is slipping away. 3I-ATLAS is closing in on the Sun, defying everything we thought we knew about comets. Instead of fleeing the inferno, it's aiming gas directly at it, provoking the very star that sustains us. Behind closed doors, experts are no longer debating what it is, but how we'll survive what comes next. Because if this cosmic anomaly awakens something hidden inside the Sun, the fallout could threaten the very fabric of our civilization. Stay with me, because the scenarios we're about to explore, as terrifying and hard to hear as they are, must be heard. If this mystery has you, the way it has me, don't let go. Hit like and subscribe so you never miss the next revelation, as this unfolds live before us. Drop a comment, tell me where you're watching from, what time your clock reads, and what you think this means for our civilization. And if you truly want to help this community rise, share this video on X, Facebook, Reddit, or just whisper it into your circles. You are the reason we keep uncovering what others don't dare to. Part 1. The image that shouldn't exist. There's an image that was released recently, and it shows something that should be impossible. A comet, or what we thought was a comet, is firing a jet of gas toward the Sun. Not away from it. Toward it. If you know anything about comets, you know this makes no sense. Comets are supposed to be nature's windsocks, their tails streaming away from the solar wind like flags in a hurricane. They heat up as they approach our star, their frozen surfaces vaporizing into space, creating those magnificent tails that always point away from the Sun. Always. Until now. The object in question is called 3I-ATLAS, and it's not from around here. It's an interstellar visitor, the third one we've ever identified coming from beyond our solar system. It was discovered on July 1st, 2025, by the ATLAS telescope in Chile, and from the moment astronomers got a good look at it, they knew something was off. The trajectory was hyperbolic, unbound to our Sun, screaming through our neighbourhood at roughly 58 to 60 kilometers per second. That's fast enough to escape the Sun's gravity entirely, which means wherever it came from it's just passing through. But it's that image, that impossible jet, that has everyone from professional astronomers to internet conspiracy theorists working overtime. Picture this for a moment. You're an astronomer, you've spent your career studying comets, and you see an object doing the exact opposite of what every textbook, every model, every observation in human history says it should do. It's like watching a river flow uphill or a ball roll up a slope on its own. The implications start small, then they grow. First, you think maybe it's an observational error. Maybe the angle is wrong, maybe it's an optical illusion created by dust and geometry. But as more data comes in, as more telescopes point at this thing, the anomaly persists. The jet appears to be real, and it appears to be directed sunward. Observatories around the world are scrambling. The James Webb Space Telescope has turned its infrared eye toward 3I-ATLAS. Hubble is watching. Ground-based giants like Gemini and the Very Large Telescope in Chile are tracking it nightly. And in the corners of the internet where people love a good mystery, the speculation has gone from 0 to 60 faster than you can say alien probe. Some are calling it a natural oddity, a weird quirk of physics we haven't encountered before. Others are suggesting something far stranger, something that crosses the line from science into science fiction. What if this isn't just a comet? What if it's something built, something designed, something that has a purpose? If you think about comets as solar wind sailboats, then 3I-ATLAS seems to be trying to become a solar harpoon. It's moving against the grain, and that raises a question that sounds absurd until you really think about it. What if this object isn't just weird? What if it's dangerous? What if, in the worst-case scenario, this interstellar visitor could actually do something to our Sun, something that ripples outward to Earth, to us, to everything we've built and everyone we love? Let me give you some context. 3I-ATLAS is not just any comet. It's classified as an interstellar object, which means it originated outside our solar system, probably ejected from another star system light years away, wandering the void between stars for who knows how long. This is only the third interstellar object we've ever detected. The first was 1I/Oumuamua in 2017, that strange cigar-shaped rock that tumbled through our system and left more questions than answers. The second was 2I/Borisov in 2019, which behaved more like a normal comet, and gave us some relief that maybe the universe wasn't as weird as Oumuamua suggested. And now we have 3I-ATLAS, and it might be the weirdest of them all. The object is on a trajectory that will bring it closest to the Sun, what astronomers call perihelion, on October 29th or 30th, 2025. That's just weeks away from the time of this recording. It won't come dangerously close by cosmic standards. At perihelion, it will be about 1.36 to 1.4 astronomical units from the Sun, which puts it somewhere between the orbits of Earth and Mars. For reference, 1 astronomical unit is the distance from Earth to the Sun, so this thing will be a bit farther out than we are. Earth itself will be about 1.8 astronomical units away from 3I-ATLAS at its closest approach, so there's no risk of collision. No need to build bunkers or stockpile canned goods just yet. But here's where it gets interesting. This isn't about physical collision. This is about influence. This is about what happens when an object from beyond our solar system, carrying unknown chemistry, unknown structure, unknown everything, gets close enough to our Sun to potentially interact with it in ways we don't fully understand. And that jet, that impossible sunward jet, is the matchstick that could light a much larger fire of consequences. So what's causing this anomaly? Is it physics we haven't accounted for? Is it a rotational quirk, the object spinning in just the right way to create an illusion? Or is it something else entirely? Something that would force us to reconsider not just this object, but the nature of what travels between the stars? If the jet is real, and if it's not just a fluke of geometry or observer bias, then we need to ask a question that feels almost ridiculous to say out loud. Who or what might be behind it? Part 2. Anatomy of an anomaly. Let's get into the weeds of what we actually know about 3I-ATLAS, because the more you learn about this thing, the stranger it becomes. First, the chemistry. When the James Webb Space Telescope pointed its infrared instruments at the object, it picked up spectroscopic data that made scientists do a double-take. The ratio of carbon dioxide to water in the comet's outgassing is one of the highest ever measured. Most comets are basically dirty snowballs, with water ice being the dominant volatile. When they heat up, they release water vapour, which creates the coma, that fuzzy cloud around the nucleus, and the tail. But 3I-ATLAS is different. It's releasing carbon dioxide at levels that dwarf its water emissions, and that tells us something about where it came from or what it's made of. Carbon dioxide-dominated comets suggest formation in extremely cold environments, or exposure to intense radiation that stripped away lighter elements. Think about it. If this object formed in another star system, it might have condensed in a region far colder than anything in our solar system, or it might have been irradiated by cosmic rays during its interstellar journey. Either way, it's carrying a chemical signature that screams not from around here. The high carbon dioxide ratio could also mean the object is older than typical solar system comets, or that it's been reprocessed somehow, heated and refrozen multiple times over eons. Then there's the water detection at absurd distances. Hydroxyl emissions, which are signatures of water molecules breaking down under solar radiation, were detected when 3I-ATLAS was about 3.5 astronomical units from the Sun. That's out near the orbit of Jupiter. At that distance, solar heating is minimal. Water ice shouldn't be sublimating in significant amounts that far out. Yet it was. That suggests either the object has an internal heat source, maybe from radioactive decay, or some kind of chemical reaction, or it's being heated by something we haven't identified. Or, and this is where speculation starts to creep in, the outgassing isn't purely natural. Size estimates for 3I-ATLAS have been all over the map. Early observations suggested a lower bound of around 0.32 to 5.6 kilometres in diameter. Not huge, but not tiny either. Later observations, as the object came closer and brightened, suggested it might be much larger, possibly 10 to 20 kilometres across. That's significant. A 10-kilometre object has a lot more mass, a lot more gravitational pull, a lot more potential energy. If it's actively outgassing, that's a lot of material being ejected into space. And if that material is being directed even partially toward the Sun, then we're talking about a non-trivial amount of stuff potentially interacting with the solar environment. The trajectory is hyperbolic, meaning 3I-ATLAS is not bound to the Sun. It's moving too fast to be captured by solar gravity. It's on a one-time flyby, here and then gone forever, unless something changes. The velocity is around 58 to 60 kilometers per second relative to the Sun, which is consistent with an interstellar origin. Objects that form in our solar system don't naturally achieve those speeds unless they're gravitationally slingshot by a planet, and the trajectory of 3I-ATLAS doesn't fit that profile. It came from interstellar space, and it will return to interstellar space. Now, about that oddity everyone's talking about. The activation of the coma and tail far from the Sun is unusual but not unheard of. Some comets, especially those with high carbon dioxide content, can start outgassing farther out because carbon dioxide sublimates at lower temperatures than water. But the shape and direction of the tail, that's where things get weird. Some analysts, including Avi Loeb, the Harvard astrophysicist who's never met a speculative idea he didn't like, have pointed to what they call an anti-sunward tail, or at least something that doesn't fit the normal pattern. In a typical comet, the tail is pushed away from the Sun by radiation pressure and the solar wind. But if the geometry is right, if the object is spinning or tumbling in a specific way, you could see jets that appear to point in unexpected directions. Here's where the natural physics explanations come in. Rotational spin could expose different surface areas to solar heating at different times, creating jets that fire in various directions depending on where the active vents are located. Fracturing of the surface could expose volatile rich layers beneath a protective crust, leading to sudden outbursts of gas that don't align with the standard sunward heating model. Thermal lag, where heat from the Sun takes time to penetrate the surface, could mean the object is releasing stored heat from a previous closer pass, or from internal processes, creating outgassing that doesn't correlate with current solar distance. But then there's the other possibility, the one that makes your skin prickle a little. What if the jet toward the Sun is intentional? What if we're not looking at a passive rock with ice on it, but something that's actively directing its exhaust? If you imagine a machine or a structure, something with thrusters or vents, ejecting material in a controlled way, what would that look like from a distance? It would look like a comet with a weird tail. It would look anomalous, but not impossible. And if that machine wanted to approach the Sun for some reason, maybe to harvest energy, maybe to study it, maybe to do something we can't even fathom, then firing a jet toward the Sun could be a form of braking, slowing itself down, adjusting its trajectory. Let me break down the jargon for you. Carbon dioxide outgassing means the object is releasing carbon dioxide gas, which happens when frozen carbon dioxide ice, also called dry ice, heats up and turns directly from solid to gas. Water outgassing is the same process but with water ice. The coma is that fuzzy cloud of gas and dust that surrounds a comet's nucleus when it gets active. It's what makes a comet look big and diffuse, instead of like a tiny point of light. Hyperbolic orbit means the object's path is open, not a closed ellipse. It's moving too fast to be trapped by the Sun's gravity, so it will pass through once and leave. So here's where we are. We have an interstellar object with strange chemistry, outgassing far from where it should, possibly showing a jet directed toward the Sun and approaching its closest point to our star in a matter of weeks. The natural explanations are plausible, but they require some assumptions. The artificial explanations are wild, but they're not physically impossible, and that's the uncomfortable space we're in. We're standing at the edge of the known, staring into the unknown, and the unknown is staring back. Part 3. The speculative explosion. Imagine you're a scientist, alone in your lab late at night. The rest of the building is dark, the only light coming from your computer screen. You're scrolling through images of 3I-ATLAS, zooming in on that jet, measuring angles, running simulations, and a thought creeps in, uninvited, unwelcome. What if this is a probe? What if something built this? You shake your head, you tell yourself it's the exhaustion talking, the caffeine wearing off. But the thought doesn't leave. It sits there, in the corner of your mind, growing. This is where we enter the realm of speculation, and it's important to say up front that what follows is hypothesis, not established fact. But science advances by asking what-if questions, by entertaining possibilities that seem absurd until they're proven true. And when it comes to interstellar objects, we're in new territory. We've only detected 3 of them. We don't know how common they are, what they're made of, or whether they're all natural. So let's entertain the idea, just for a moment, that 3I-ATLAS is not entirely natural. Avi Loeb, who directs the Galileo project at Harvard, has made a career of suggesting that interstellar objects might be artificial. He argued that Oumuamua could have been a light sail, a thin reflective sheet pushed by starlight sent by an alien civilization. The scientific community largely disagreed, favouring natural explanations like a nitrogen iceberg or a hydrogen comet. But Loeb's point was valid. If we assume we're alone in the universe, we'll interpret everything through that lens. If we allow for the possibility that we're not alone, then some observations might have alternate explanations. So let's apply that thinking to 3I-ATLAS. What if it's a machine? What if the jet toward the sun is not an accidental quirk of physics but an intentional action? One hypothesis, and again this is highly speculative with no proof, is that the object could be harvesting solar energy. Stars are the most powerful energy sources in the universe. A civilization capable of interstellar travel might send probes to stars to collect energy, maybe to power themselves, maybe to store it, maybe to redirect it. The jet could be a cooling system, a way to manage the heat absorbed from being near the sun, or it could be a particle accelerator, shooting material into the solar wind to create a feedback loop of energy extraction. Another idea, even wilder, is that 3I-ATLAS is a fragment of a megastructure, something like a Dyson swarm, which is a collection of solar panels or habitats orbiting a star to capture its energy. Dyson swarms are theoretical constructs proposed by physicist Freeman Dyson in the 1960s. If one existed around another star, and if it was damaged or decommissioned, fragments could be ejected into interstellar space. A chunk of a Dyson swarm, still partially functional, could be on an uncontrolled trajectory, and if it happened to pass through our solar system, it might automatically orient itself toward the nearest star, our Sun, as it was designed to do. Then there's the signal injection theory. What if the object isn't mining the Sun, but triggering it? What if it's designed to inject particles or energy into the solar plasma to spark a solar event? This sounds like science fiction, but consider the physics. The Sun is a massive ball of plasma held together by gravity and regulated by magnetic fields. It's in a constant state of barely controlled chaos. Coronal mass ejections, solar flares, sunspots, these are all manifestations of magnetic instabilities. If you could introduce the right kind of disturbance at the right place, you might be able to trigger a larger event. It's like pushing a boulder balanced on a cliff. The boulder has enormous potential energy, but all it needs is a small nudge to release it. Why would anyone want to trigger a solar event? Maybe it's a signal, a way to announce presence. Maybe it's a test, to see how a star responds. Maybe it's a weapon, though that raises the question of why target our sun specifically. Or maybe it's not intentional at all. Maybe the object is a derelict, a broken machine that's been drifting for eons, and its proximity to the sun is reactivating old programming in ways that were never intended. Let's compare 3I-ATLAS to its interstellar predecessors. Oumuamua was strange because it accelerated slightly as it left the solar system, as if pushed by an unseen force. The natural explanation was outgassing, but Oumuamua showed no visible coma or tail, which made the outgassing hypothesis awkward. It was also shaped oddly, either elongated like a cigar or flat like a pancake, depending on how you interpreted the light curve data. 2I/Borisov, on the other hand, was refreshingly normal. It looked like a comet, acted like a comet, had the chemistry of a comet. It reassured us that not everything from beyond our solar system is weird, and now we have 3I-ATLAS, which might be the weirdest of all. High carbon dioxide, early activation, possible sunward jet, large size, fast velocity. It's checking boxes we didn't even know existed. If alien technology exists, and that's a big if, hiding it as a comet would be the perfect stealth mode. Comets are common. Our solar system has trillions of them in the Oort cloud. An interstellar object that looks like a comet wouldn't raise alarms unless you looked closely. It could pass through, do whatever it was designed to do, and leave before anyone realised it was anything other than a random chunk of ice and rock. The perfect disguise is to be something boring, something expected, something that blends into the background noise of the cosmos. Even if the artificial hypothesis is wrong, even if 3I-ATLAS is entirely natural, the fact that we're entertaining these ideas tells you something about where we are as a species. We've reached a point where the universe is no longer a static backdrop. It's an active participant in our story. Objects come from beyond, carrying information, carrying matter, carrying possibilities. And some of those possibilities are uncomfortable. They challenge our assumptions. They make us wonder if we're as alone as we think, or as safe as we hope. Part 4. Solar Vulnerability, a Primer for the Paranoid. Let's talk about the Sun, because understanding what 3I-ATLAS might do requires understanding what our star is capable of. The Sun is not a benign ball of light. It's a roiling, churning, magnetically unstable fusion reactor 93 million miles away, and it's the reason we exist. but it's also the reason we could stop existing. The sun has moods, and when it's in a bad mood, Earth feels it. Coronal mass ejections, or CMEs, are one of the sun's most dramatic tantrums. These are massive bursts of plasma and magnetic field that erupt from the solar corona and race outward into space. When a CME hits Earth, it compresses our magnetosphere, the magnetic bubble that shields us from solar wind, and can induce electrical currents in power grids, pipelines, and communication cables. In 1859, a massive CME hit Earth in what's now called the Carrington event. Telegraph systems worldwide went haywire. Some operators reported shocks, and auroras were seen as far south as the Caribbean. If a Carrington-scale event happened today, it could cause trillions of dollars in damage, knock out power grids for months, disrupt satellites, and cripple GPS navigation. The sun operates on an 11-year cycle of activity, oscillating between solar minimum and solar maximum. At solar minimum, the sun is relatively quiet, with few sunspots and fewer CMEs. At solar maximum, the surface is pockmarked with sunspots, and CMEs and solar flares are frequent. We're currently in solar cycle 25, which began around 2019 and is expected to peak around 2025. That means we're right in the window of maximum solar activity, which is both a blessing and a curse. A blessing because solar maximum gives us spectacular auroras and lots of data to study. A curse because it increases the risk of space weather events that can affect our technology-dependent civilization. Geomagnetic storms are the Earth-based consequence of solar activity. When charged particles from a CME interact with Earth's magnetosphere, they can cause fluctuations in the magnetic field. These fluctuations induce currents in long conductors like power lines. If the current is strong enough, it can damage transformers, which are expensive and take months to replace. In 1989, a geomagnetic storm caused a 9-hour blackout in Quebec, Canada, affecting 6 million people. In 2003, a series of storms called the Halloween storms damaged satellites, disrupted airline communications, and caused auroras visible from the southern United States. Now let's tie this to 3I-ATLAS. Could an interstellar object, by behaving oddly, tip the balance of solar activity? Here's where we move into speculative territory, but it's grounded in plausible physics. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the sun. It's relatively tenuous, but it carries energy and momentum. If 3I-ATLAS is outgassing as it approaches perihelion, it's ejecting material into the solar wind. That material, gas and dust, could add to the particle density in the inner solar system. More particles mean more potential for interactions. Charged particles from the comet's outgassing could also interact with the sun's magnetic field. The sun's magnetic field extends far into space, carried by the solar wind in a structure called the interplanetary magnetic field. If 3I-ATLAS is ejecting ions, electrically charged atoms, those ions become part of the magnetic environment. In the right conditions, they could trigger magnetic reconnection, a process where magnetic field lines break and reconnect, releasing energy. Magnetic reconnection is what powers solar flares and some CMEs. It's a sudden, explosive release of stored magnetic energy. Could 3I-ATLAS inject enough material or charged particles to trigger a significant solar event? Probably not. The sun is enormous, and the comet is tiny by comparison. But the sun is also a complex non-linear system. In non-linear systems, small inputs can sometimes have outsized outputs, especially if the system is already near a tipping point. It's like a controlled burn in a forest. Most of the time, it goes as planned. But if conditions are just right, dry enough, windy enough, a small controlled fire can become a wildfire. If the sun is already primed for a CME, if magnetic energy is already building up in a sunspot region, then an external perturbation, even a small one, might be the nudge that releases it. Mainstream solar physicists would say the probability of 3I-ATLAS causing a major solar event is extremely low, and they're probably right. The comet's mass and outgassing rate, while significant by comet, standards are negligible compared to the sun's total mass and energy output. But here's why we talk about it anyway. The stakes are high. Our civilization is more dependent on technology than ever before. Satellites, GPS, power grids, the internet, all of it is vulnerable to space weather. A major geomagnetic storm could disrupt daily life in ways we're not prepared for. So even if the probability is low, the consequence is high, and that's a combination that warrants attention. Let's break down worst case versus likely case. The likely case is that 3I-ATLAS approaches perihelion, outgasses normally or abnormally, provides scientists with interesting data, and then leaves the solar system without causing any noticeable effects on Earth. The worst case is that the comet, either through natural processes or something more exotic, contributes to a solar event that results in a moderate to severe geomagnetic storm. Power outages, satellite damage, GPS disruptions, communication blackouts. Not civilization ending, but civilization disrupting. And in a world where supply chains are fragile and just-in-time delivery is the norm, even a few days of disruption can cascade into larger problems. The countdown is on. 3I-ATLAS is approaching perihelion, and what happens in late October 2025 may or may not mark a turning point. But even if nothing happens, even if the comet passes quietly, we'll have learned something. We'll have learned that interstellar visitors are more common than we thought, that they can behave in unexpected ways, and that our models need updating. And if something does happen, if we see a solar event coinciding with the comet's closest approach, then we'll have a data point that forces us to reconsider the Sun's vulnerability to external influences. Part 5. Countdown to perihelion. The discovery of 3I-ATLAS happened on July 1st, 2025, when the ATLAS telescope in Chile captured images of a fast-moving object with an unusual light curve. ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, is designed to detect near-Earth objects that could pose collision risks. It wasn't looking for interstellar visitors, but it found one anyway. Follow-up observations confirmed the hyperbolic trajectory, and within days astronomers around the world were scrambling to observe this new arrival. The trajectory details are critical. 3I-ATLAS is on a path that will bring it closest to the Sun at perihelion on October 29th or 30th, 2025. The exact date depends on how you model the comet's outgassing, which can create a small but noticeable thrust, like a rocket engine. At perihelion, the comet will be approximately 1.36 to 1.4 astronomical units from the Sun. To put that in perspective, Earth orbits at 1 astronomical unit, Mars at 1.5, so 3I-ATLAS will be in the inner solar system, closer to the Sun than Mars, but not dramatically closer than Earth. It's not a sungrazer, one of those comets that plunges to within a few solar radii and often disintegrates. It's keeping a respectful distance. Earth's closest approach to 3I-ATLAS will occur around the same time frame, with the comet about 1.8 astronomical units away. That's roughly the distance from the Sun to Mars. There's no risk of collision, no chance of debris hitting our planet. The comet's trajectory doesn't intersect Earth's orbit, but distance isn't the only factor. If 3I-ATLAS does something to the Sun, if it triggers a CME or a solar flare, distance becomes less relevant. Solar radiation and charged particles travel fast. A CME can reach Earth in as little as 15 to 18 hours if it's aimed directly at us. Observatories are mobilizing for the perihelion event. The James Webb Space Telescope, with its infrared capabilities, can study the comet's composition, temperature, and outgassing patterns in exquisite detail. Hubble Space Telescope, though older, still has sharp eyes and can track the comet's coma and tail structure. The Spherix mission, set to launch in 2025, is designed to study the sky in infrared and could provide additional data. Ground-based observatories like the Gemini telescopes in Hawaii and Chile, and the Very Large Telescope in Chile, are some of the most powerful instruments on Earth, capable of high-resolution spectroscopy and imaging. What will scientists watch for as 3I-ATLAS approaches perihelion? First, an increase in outgassing activity. As the comet gets closer to the Sun, solar heating should increase, which should lead to more gas and dust being released. If the outgassing increases dramatically, it could indicate the comet is fracturing or exposing new volatile rich layers. Second, tail formation. The structure, direction, and composition of the tail will tell us about the comet's chemistry and the forces acting on it. If the tail shows unexpected features, like jets pointing in odd directions, that's data worth analysing. Third, brightness changes. Comets can brighten or dim unpredictably, sometimes due to outbursts of activity, sometimes due to changes in observing geometry. A sudden brightening could mean the comet is fragmenting, which would be both spectacular and scientifically valuable. Fourth, trajectory deviations. If the comet's outgassing is strong enough, it can act like a rocket, altering the comet's path slightly. Measuring these deviations can tell us about the outgassing rate and the comet's mass. Fifth, jets. Some comets produce narrow jets of gas and dust from active vents on their surface. Observing the number, location, and behaviour of jets can reveal information about the comet's rotation, surface structure, and internal heat sources. Now, the speculative angle. If the jet toward the Sun becomes stronger as the comet approaches perihelion, what might we see? One possibility is a visible effect on the Sun itself. This is extremely unlikely, but let's entertain it. If the comet ejects enough charged particles, and if those particles reach the Sun and interact with its magnetic field, you could theoretically see a localized brightening or disturbance in the solar corona. Another possibility is an enhanced tail. If the outgassing increases, the tail could become brighter and more extensive, potentially visible to amateur astronomers on Earth. There's also the meteor shower possibility. If 3I-ATLAS is shedding significant amounts of dust, and if Earth passes through that dust stream, we could see a meteor shower. The timing would depend on the geometry of the comet's orbit and Earth's orbit. It's a long shot because the comet isn't passing close to Earth's orbital path, but it's not impossible, and if we did see meteors, it would confirm that the comet is shedding material, which would support the idea that it's an active, outgassing comet rather than a dormant rock. The watch window extends from late October through early December. After perihelion, 3I-ATLAS will pass behind the Sun from our viewpoint, a period called solar conjunction. During conjunction, we can't observe the comet because it's too close to the Sun in the sky. The glare overwhelms the signal. After conjunction, the comet will emerge on the other side, moving away from the Sun and heading back into interstellar space. That post-conjunction period will be critical. If the comet has fragmented or changed significantly, we'll see it then. We've seen the object, we know it's headed for the Sun. The question is what will happen. Will it be anticlimactic, just another comet doing comet things in a slightly unusual way? Or will it be a turning point, an event that challenges our understanding of interstellar objects, solar dynamics, or even the possibility of artificial constructs travelling between stars? The universe has a habit of surprising us, and 3I-ATLAS is in position to deliver one of those surprises. Part 6. The History of Rogue Visitors. Before 3I-ATLAS, there were two interstellar objects that entered our solar system, made a brief appearance, and left us with more questions than answers. Understanding them helps us understand what makes the third visitor so strange. 1I/Oumuamua arrived in October 2017. It was spotted by the Pan-STARRS telescope in Hawaii, and within days astronomers realised it was moving too fast to be bound to the Sun. The name Oumuamua means scout, or messenger, in Hawaiian, fitting for the first known interstellar object. What made Oumuamua bizarre was its shape and behaviour. Based on how its brightness varied as it tumbled, scientists calculated it was either very elongated, like a cigar, or very flat, like a pancake. Both shapes are unusual for natural objects, which tend to be more spherical due to gravity. Oumuamua also accelerated slightly as it left the solar system, as if pushed by a force we couldn't see. The most likely explanation was outgassing, but Oumuamua showed no visible coma or tail, which made the outgassing hypothesis awkward. Some scientists suggested it was a hydrogen iceberg, which would outgas invisibly. Others suggested it was a nitrogen iceberg, a chunk of frozen nitrogen from a Pluto-like exoplanet. And then Avi Loeb suggested it could be a light sail, a thin reflective sheet pushed by starlight, possibly built by an alien civilization. That hypothesis was controversial, to put it mildly, but it opened the door to thinking about interstellar objects as potentially artificial. 2I/Borisov arrived in August 2019. It was discovered by amateur astronomer Gennady Borisov in Crimea, and it was immediately clear it was interstellar. But unlike Oumuamua, Borisov behaved like a normal comet. It had a coma, a tail, it outgassed water and carbon monoxide, and its chemistry matched what you'd expect from a comet that formed in another star system, but under similar conditions to our solar system comets. Borisov was reassuring. It told us that not everything from beyond is weird, that other star systems produce comets much like ours, and that interstellar space is filled with objects we can understand. And now we have 3I-ATLAS. It's larger than Oumuamua, more chemically extreme than Borisov, and potentially more active than either. The patterns are starting to emerge, or maybe the lack of patterns is the pattern. Interstellar objects don't conform to a single template. They're diverse. carrying the fingerprints of their origin systems, their journeys, and the forces they encountered along the way. The speeds are telling. All 3 objects entered the solar system at velocities consistent with being unbound to any star. Oumuamua was moving at roughly 26 km per second relative to the Sun. Borisov was at 32 km per second. 3I-ATLAS is at 58 to 60 km per second, significantly faster. Higher speeds suggest longer distances travelled or more energetic ejection events. If 3I-ATLAS was ejected from its home system by a close encounter with a massive planet or a stellar flyby, it could have been accelerated to these speeds, or it could have been wandering the galaxy for so long that it picked up speed from gravitational interactions along the way. The chemical compositions are equally diverse. Oumuamua's composition remains a mystery because we didn't get good spectroscopy before it left. Borisov showed carbon monoxide and water, typical comet chemistry. 3I-ATLAS shows a carbon dioxide-dominated signature with water present but secondary. This suggests a formation environment colder than what Borisov experienced, or post-formation processing that altered the chemistry. If 3I-ATLAS formed in a molecular cloud, a region of dense gas and dust between stars, it could have incorporated more carbon dioxide. Or if it spent time near a massive star, ultraviolet radiation could have photo-dissociated water ice, leaving behind more stable carbon dioxide. Size estimates vary, but 3I-ATLAS might be the largest of the 3. Oumuamua was estimated at a few hundred meters. Borisov was around half a kilometer. 3I-ATLAS might be 10 to 20 kilometers, making it comparable to some of the larger comets in our solar system. Larger size means more mass, more gravitational binding energy, more potential for complex internal structure. If 3I-ATLAS is indeed that large, it's less likely to fragment easily, and more likely to survive perihelion intact. Are these objects random wanderers, or are they part of a larger phenomenon? One hypothesis is that interstellar space is filled with rogue planets, comets, and asteroids ejected from their home systems during planetary formation. Simulations suggest that for every star system, there might be dozens or hundreds of objects kicked out into the galaxy. If that's true, then interstellar objects should be passing through our solar system all the time. We just never had the telescopes sensitive enough to spot them until recently. The idea of an interstellar comet population is both exciting and unsettling. Exciting because it means we have samples from other star systems literally coming to us, delivering information about exoplanetary chemistry and formation conditions. Unsettling because it raises questions about what else might be out there. If comets and asteroids are common, what about larger objects? What about rogue planets wandering the void? What about structures or machines sent intentionally? 3I-ATLAS might differ significantly from its predecessors in ways that point to a broader diversity of interstellar objects than previously thought. The high carbon dioxide ratio suggests formation in conditions we don't see in our solar system. The potential sunward jet suggests dynamics we haven't observed before. The large size suggests it might be a fragment of something even bigger, broken off by collision or tidal forces during its long journey. There's also the possibility that we're dealing with streams of debris from galactic events. Imagine a star system disrupted by a supernova, or 2 stars colliding, or a planet torn apart by tidal forces. The debris would be scattered into interstellar space, creating streams of objects all following similar trajectories. If 3I-ATLAS is part of such a stream, there might be more objects like it, approaching from the same direction, carrying similar chemistry. We just haven't detected them yet. The speculative angle grows darker when you consider payloads. If interstellar objects can carry water, organics, and complex chemistry, what's to say they couldn't carry other things? Microbes, frozen and dormant, waiting for the right conditions to revive. Radiation sources, isotopes, that don't exist naturally in our solar system. Or, in the wildest scenarios, machines, probes, or data storage devices built by intelligences we can't even imagine. 3I-ATLAS could be one of thousands of such objects, most passing undetected, some noticed but ignored, and a rare few like this one behaving oddly enough to grab our attention. The catalogue of interstellar visitors is still tiny, 3 confirmed objects in less than a decade, but detection technology is improving. The Vera Rubin Observatory, which began operations in 2024, will scan the entire visible sky every few nights, detecting faint, fast-moving objects that previous surveys would have missed. NASA's NEO Surveyor mission, focused on near-Earth objects, will also catch interstellar passers-by. Within a decade, we might have dozens of confirmed interstellar objects, enough to start drawing statistical conclusions about their populations, origins and behaviours. 3I-ATLAS might be the one that breaks the mould, the one that forces us to rethink not just interstellar threats, but interstellar opportunities. If it's carrying information, chemistry or structures from another star system, studying it could teach us things we couldn't learn any other way. But if it's carrying risks, whether biological, energetic, or something else entirely, then we need to understand those risks before the next one arrives. Part 7. When comets aim at stars. Comets that approach stars closely are called sun grazers, and they're some of the most dramatic objects in the solar system. Comet Lovejoy survived a pass within 140,000 kilometres of the Sun's surface in 2011, emerging battered but intact. The SOHO spacecraft, a solar observatory launched in 1995, has discovered over 4,000 comets, most of them sun grazers that plunged into the Sun and vaporized. These comets follow trajectories that bring them incredibly close to the solar surface, within a few solar radii, where temperatures soar into the millions of degrees. The typical behaviour of a sun grazer is predictable. As it approaches the Sun, solar radiation heats the surface, causing ice to sublimate. The gas and dust are blown away from the Sun by radiation pressure and the solar wind, creating a magnificent tail that always points away from the Sun. Some sun grazers survive the encounter, their cores remaining intact even as their outer layers boil away. Others disintegrate entirely, torn apart by tidal forces or simply vaporized by the intense heat. But in all cases the tails point away, driven by the outward pressure of light and particles from the Sun. So why would 3I-ATLAS show a jet toward the Sun? Let's explore the technical reasons first. The orientation of the jet depends on where the active vents are located on the comet's surface. If the comet is rotating, and if a vent happens to be on the sunward side when it's active, the jet would point toward the Sun. But that's not the same as a tail pointing sunward. Jets are localized, narrow streams of gas and dust. Tails are large, diffuse structures shaped by solar wind and radiation pressure. You can have jets pointing in all directions, but the tail should still point away from the Sun. Another technical consideration is the geometry of observation. If you're viewing a comet from a specific angle, a tail that's actually pointing away from the Sun might appear, due to projection effects, to be pointing in an unexpected direction. Imagine looking at a flag from the side. It clearly points downwind. Now imagine looking at it from an angle where the pole is between you and the flag. It might look like the flag is pointing toward you, even though it's still pointing downwind. The same projection effect can confuse observations of comet tails. Then there's the interplay of forces. Solar wind pressure pushes gas outward. Radiation pressure pushes dust outward. But the comet's own outgassing creates local pressure that can push material in any direction. If the outgassing is strong enough, it can overcome radiation pressure temporarily, creating jets that don't align with the expected anti-sunward direction. The spin axis orientation matters too. If the comet is spinning with its axis tilted relative to the Sun, the jets will fire in a pattern that rotates with the spin, creating a spiral or corkscrew structure that, when viewed from certain angles, might look unusual. But what if the observed jet is not an illusion or a quirk of geometry? What if it's real? And what if it's pointing sunward for reasons we don't yet understand? This is where exotic physics enters the picture. Magnetic reconnection is a process where magnetic field lines break and reconnect, releasing stored energy. It happens in the Sun's corona, in Earth's magnetosphere, and potentially in the environment around a comet. If 3I-ATLAS is embedded in the Sun's magnetic field, and if its outgassing is creating a local magnetic disturbance, you could have reconnection events that accelerate particles in unexpected directions, including sunward. Charged dust particles could also interact with the Sun's magnetic field in ways that standard models don't account for. Dust grains ejected from a comet can become electrically charged due to exposure to ultraviolet light and the solar wind. Charged particles respond to magnetic fields, and if the magnetic field geometry is right, those particles could be deflected or accelerated toward the Sun instead of away from it. This would require a specific alignment of field lines and particle velocities, but it's not impossible. Now let's consider the engineering hypothesis. If 3I-ATLAS is not entirely natural, if there's some artificial component to it, then a jet toward the Sun could be intentional. Think about how a spacecraft uses thrusters. To slow down, you fire engines in the direction you're moving. To speed up, you fire them opposite. If the object wanted to adjust its trajectory to fine-tune its approach to the sun, firing a jet toward the sun would create a thrust vector that pushes the object away slightly, effectively braking. This is speculative, but it's consistent with what we'd expect from a machine capable of controlled propulsion. There's also the solar sail reverse thrusting concept. A solar sail uses radiation pressure from sunlight to propel itself. The sail is pushed away from the sun. But if you angled the sail just right, or if you had a mechanism to reflect light back toward the sun, you could create a thrust component toward the sun. It's counterintuitive, but it's possible with the right geometry and materials. The exotic chemistry possibility ties back to 3I-ATLAS's high carbon dioxide content. Carbon dioxide outgassing produces different dynamics than water outgassing. Water vapor is lighter, moves faster, and is more easily pushed by radiation pressure. Carbon dioxide is heavier, moves slower, and might not be pushed as effectively. If the comet is releasing primarily carbon dioxide, its tail structure could be different from typical water-dominated comets. The particles might stay closer to the nucleus, or they might form a denser, more compact tail that doesn't extend as far. From certain viewing angles, this could create the appearance of material moving sunward when it's actually just not moving away as fast as expected. Let's tie this to the risk scenario. If material from 3I-ATLAS is being ejected toward the sun, even in small amounts, that changes the local solar environment. The solar wind is a flow of particles, and introducing additional particles into that flow can create turbulence, density variations, and magnetic disturbances. It's like throwing pebbles into a stream. One pebble doesn't change the stream much, but a steady stream of pebbles can create ripples, eddies, and even redirect the flow slightly. Could that dust or gas cloud, if it's substantial enough, trigger reconnection events in the solar corona? Could it seed instabilities that grow into solar flares or coronal mass ejections? The honest answer is we don't know. Solar physics is complex, non-linear, and not fully understood. We have models, but models are simplifications. They can't account for every possible interaction, especially if the interaction involves something we've never observed before, like material from an interstellar object being injected into the solar wind near the sun. Whether natural or engineered, the behaviour of 3I-ATLAS opens the door to scenarios where comets aren't passive. They're not just frozen relics drifting through space, subject to the whims of gravity and solar heating. They could be active agents, influencing their environment, interacting with the solar wind and magnetic fields in ways that have consequences beyond their immediate vicinity. And if that's true, then understanding comets, especially interstellar ones, becomes not just a scientific curiosity, but a practical necessity. Part 8. Hidden Angles. Military, Intelligence, and Cover-ups. Let's shift gears and ask a darker question. What if governments and intelligence agencies are tracking 3I-ATLAS more closely than they're willing to admit publicly? What if there are classified observations, restricted data, conversations happening in secure facilities that the rest of us will never hear? This isn't about paranoia. This is about recognizing that space has always been militarized, that nations compete for strategic advantage, and that an anomalous object approaching the sun might be of interest to more than just astronomers. Consider the infrastructure we have in space. Military satellites monitor Earth's surface for missile launches, troop movements, nuclear tests. GPS satellites provide positioning data crucial for both civilian and military operations. Communication satellites relay encrypted messages between military installations worldwide. Solar observatories, both space-based and ground-based, track space weather because geomagnetic storms can disable satellites and disrupt communications. If something in space threatens any of that infrastructure, it becomes a national security issue. 3I-ATLAS, with its unusual behaviour, would absolutely be on the radar of defence agencies. Not because anyone seriously thinks it's a weapon, but because its behaviour is anomalous, and anomalies require investigation. If the object is artificial, even partially, that's information of enormous strategic importance. If it's natural but capable of triggering solar events, that's also strategically relevant. A solar storm that knocks out satellites affects everyone, but it affects military readiness more than most. Are there specialised observatories, military or intelligence operated, that track the sun and have gone dark or changed protocols recently? The answer is almost certainly yes to the first part, and we wouldn't know about the second part. The United States has the Defense Support Program and the Space-Based Infrared System, satellites designed to detect missile launches by spotting their infrared signatures. Those same satellites can also observe the sun and solar phenomena. Other nations, Russia, China, have their own space surveillance networks. If any of them detected something unusual about 3I-ATLAS, would they share that information publicly? Maybe, maybe not. It depends on whether sharing serves their interests. There's precedent for information withholding in space observations. During the Cold War, both the US and Soviet Union detected phenomena in space that weren't immediately explained. Some were later identified as natural, like gamma-ray bursts, which were initially detected by military satellites monitoring for nuclear tests. Others remained classified for years. The point is, not everything observed in space is immediately shared with the public or the scientific community. Could 3I-ATLAS be of interest not just to astronomers, but to defense agencies? Absolutely. If there's even a remote possibility that the object is artificial, that raises questions about who built it, why, and whether there are more like it. If it's natural but behaving in ways that could affect solar activity, that's relevant to space weather forecasting, which is critical for protecting satellite infrastructure. Defense agencies would be foolish not to pay attention. Could there be deliberate information withholding about what's being observed near the sun? This is where we tread carefully, because there's a difference between reasonable operational security and conspiracy theories. Governments classify information for legitimate reasons, protecting sources, methods, and capabilities. If a classified satellite observed 3I-ATLAS and detected something unusual, that data might not be shared publicly, because sharing it would reveal the satellite's capabilities. But that doesn't mean there's a cover-up in the sinister sense. It just means information is compartmentalized. That said, there have been instances where solar observatories experienced unexplained downtime. In September 2018, the National Solar Observatory at Sunspot, New Mexico was evacuated and closed for over a week without explanation. Rumours swirled about everything from alien signals to security threats. The eventual official explanation was that the closure was related to an FBI investigation into an employee, but the lack of immediate transparency fueled speculation. Whether or not that incident is related to anything we're discussing here, it illustrates that solar observatories can become subjects of scrutiny for reasons beyond pure science. Let's tie this back to the sun jet image. If 3I-ATLAS is ejecting material toward the sun, and if that material is interacting with the solar environment in measurable ways, then agencies responsible for space weather forecasting would want to know. The National Oceanic and Atmospheric Administration, NOAA, runs the Space Weather Prediction Center, which monitors solar activity and issues forecasts and warnings. If 3I-ATLAS is considered a potential factor in solar activity, even a minor one, NOAA would be tracking it. But would they share every detail with the public? Probably not, especially if the data is preliminary or uncertain. The vulnerability of global infrastructure to solar storms is well documented. In 2012, a massive coronal mass ejection missed Earth by about 9 days. If it had hit, it would have been comparable to the Carrington event, potentially causing widespread power outages, satellite failures, and trillions in economic damage. That near miss prompted increased investment in space weather monitoring and preparedness. It also likely prompted classified discussions about how to protect critical infrastructure, and those discussions would have involved defense and intelligence agencies. If 3I-ATLAS is perceived as a wild card, an object that might influence solar activity in unpredictable ways, then it's not unreasonable to think that classified analysis is happening. The question is whether that analysis has found anything worth hiding, or whether the secrecy is simply standard procedure. Without access to classified data, we can't know. But we can ask the questions, and we can pay attention to what's not being said as much as what is. There's a micro-story worth sharing here, possibly apocryphal, possibly not. An astronomer working late one night noticed unusual data from a solar monitoring station. Nothing dramatic, just a brief dropout in telemetry, followed by a resumption. When the astronomer reached out to colleagues at the monitoring station, the response was vague. Technical difficulties, nothing to worry about. But the timing was odd. It coincided with 3I-ATLAS entering a certain region of space relative to the Sun. Was it coincidence? Probably, but coincidences are what drive people to dig deeper, to ask harder questions. whether the object carries life, radiation, or energetic danger, these are the biological and energetic nightmares we'll explore next. Because even if 3I-ATLAS is entirely natural, even if there's no military interest and no cover-up, the potential for it to carry exotic materials or trigger unexpected events remains, and that potential is worth examining, even if it takes us into uncomfortable territory. Part 9. Biological and energetic nightmares. There's a theory in astrobiology called panspermia, and it suggests that life, or at least the ingredients for life, can spread between star systems on comets and asteroids. The idea is simple. A comet forms in a planetary system, incorporates water and organic molecules, maybe even microbes if life exists there. Then that comet is ejected, either by gravitational interactions with planets or by a catastrophic event like a supernova. It spends millions or billions of years in interstellar space, frozen, dormant, shielded from radiation by its icy exterior. Eventually it enters another star system, ours, for example. As it approaches the sun, it warms up, the ice sublimates, and whatever was trapped inside, microbes, organic molecules, exotic isotopes, is released into the inner solar system. Is this plausible? Scientifically, yes. Microbes have been shown to survive in space conditions for limited periods. Experiments on the International Space Station have exposed bacteria to vacuum, ultraviolet radiation, and cosmic rays, and some survived. Tardigrades, tiny creatures that look like 8-legged bears under a microscope, can survive even harsher conditions, entering a state called cryptobiosis, where their metabolism essentially stops. They can be frozen, dehydrated, irradiated, and still revive when conditions improve. If Earth life can do that, it's reasonable to think life elsewhere might have similar capabilities. Comets carry organic compounds. We know this from spectroscopy and from sample return missions like Stardust, which captured dust from Comet Wild 2 and brought it back to Earth. The dust contained amino acids, the building blocks of proteins. If comets forming in our solar system have organics, comets from other star systems probably do too. The question is whether they carry anything more complex, anything alive. Let's link this to 3I-ATLAS. If it originated from another star system billions of years ago, it's been travelling through interstellar space for an unimaginable length of time. Cosmic rays, high-energy particles from supernova remnants and other sources would have bombarded it constantly. Radiation damages DNA, breaks chemical bonds, kills cells. But if the comet's interior remained frozen, shielded by meters of ice and rock, then anything buried inside might have been protected. As the comet approaches the sun and begins outgassing, that interior material gets exposed. Could alien microbes survive the journey and be released into our solar system? It's an extreme scenario, but not physically impossible. The microbes would need to be hardy, capable of surviving radiation doses far beyond what Earth life experiences. They would need to remain viable after billions of years in stasis, and they would need to survive the violent process of outgassing, where temperatures and pressures fluctuate wildly. Those are tall orders, but evolution is creative. If life exists elsewhere, it might have evolved mechanisms we can't imagine. Now, what happens if exotic microbes enter the inner solar system? They're released by 3I-ATLAS as it outgasses. They're carried by the solar wind, a stream of charged particles flowing outward from the sun. Some would be blown into interstellar space. Some would be swept inward, toward the sun itself, where they'd be incinerated. But some, caught in eddies and magnetic field lines, might end up in orbits that intersect Earth's path. Months or years later, Earth passes through that region of space, and the microbes, or their remnants, enter our atmosphere. Most would burn up. Atmospheric entry is violent. Frictional heating would destroy anything fragile. But some meteors survive entry, landing as meteorites, and if microbes were embedded in dust particles with the right properties, they might survive too. They'd land on Earth's surface, in oceans, on land, in ice. And if they're viable, if they can metabolize and reproduce in Earth's environment, then you have the beginning of a panspermia event. Alien biology interacting with Earth biology. The consequences are unpredictable. Maybe the alien microbes can't compete with Earth life and die off immediately. Maybe they fill a niche that Earth life hasn't occupied and coexist peacefully. Or maybe they're invasive, outcompeting native species, disrupting ecosystems, causing extinctions. Or maybe they carry biochemistry so different from ours that they don't interact with Earth life at all, existing in parallel like two ships passing in the night. Then there's the darker possibility. What if the alien microbes are pathogenic? What if they infect humans, animals, plants, causing diseases we have no immunity to? This is the plot of countless science fiction stories, but it's rooted in real biology. When Europeans arrived in the Americas, they brought diseases like smallpox and measles that devastated indigenous populations who had no prior exposure. Alien microbes would be the ultimate invasive species, and we'd have zero natural defences. But let's be clear, the probability of this scenario is extremely low. First, the comet would have to carry viable microbes. Second, those microbes would have to survive outgassing and solar wind exposure. Third, they'd have to reach Earth. Fourth, they'd have to survive atmospheric entry. Fifth, they'd have to be compatible enough with Earth's environment to survive and reproduce. Each of those steps is a filter, and the combined probability is vanishingly small. But it's not zero. There's another angle to this nightmare, one that's less biological and more energetic. Suppose 3I-ATLAS is carrying exotic isotopes, elements that don't exist naturally in our solar system, or exist only in trace amounts. Isotopes are variants of elements with different numbers of neutrons. Some are stable, some are radioactive. If the comet formed in an environment enriched with certain isotopes, maybe near a supernova remnant or a neutron star, it could be carrying radioactive material. As the comet outgasses, those isotopes get released into the solar wind. They're carried throughout the inner solar system. They decay, emitting radiation, alpha particles, beta particles, gamma rays. Most of this radiation wouldn't reach Earth's surface, blocked by our atmosphere and magnetosphere. But satellites in orbit, astronauts on the International Space Station, they'd be exposed. High-energy particles could damage satellite electronics, degrade solar panels, increase radiation doses for crew members. There's also the possibility that 3I-ATLAS triggers a solar event, and the fallout is increased radiation reaching Earth. Solar flares and coronal mass ejections accelerate particles to near light speed. When those particles reach Earth, they're funneled by our magnetic field toward the poles, where they collide with atmospheric molecules and create auroras. But they also increase radiation levels at high altitudes. Airline pilots and flight attendants, who spend significant time at 30,000 feet, receive higher radiation doses during solar storms. A strong enough storm could ground flights, not because of immediate danger, but as a precaution. Then there are the subtle biological effects. Increased cosmic ray flux has been correlated with changes in cloud formation. Cosmic rays ionize air molecules, which can act as condensation nuclei for water vapour, forming clouds. More clouds mean changes in Earth's climate. Some studies suggest links between cosmic ray intensity and climate oscillations, though the mechanisms are debated. If 3I-ATLAS contributes to increased particle flux in the inner solar system, even temporarily, it could have subtle effects on Earth's climate and weather patterns. There's also the question of mutation rates. Radiation causes mutations by damaging DNA. Most mutations are harmful or neutral, but occasionally they're beneficial. Increased radiation from solar events could, in theory, increase mutation rates in organisms exposed to it. For humans, most of us are shielded by buildings in the atmosphere, so the effect would be minimal. But for microorganisms, especially bacteria and viruses that reproduce quickly, increased mutation rates could accelerate evolution. New strains of bacteria, new variants of viruses, could emerge faster than usual. This is all highly speculative, threading together loosely connected scientific concepts into a narrative that's more fiction than fact. But it's useful to explore these ideas, not because they're likely, but because they illustrate the range of possible consequences when an interstellar object interacts with our solar system. We tend to think of comets as inert, as cosmic snowballs that are interesting to study, but fundamentally harmless. 3I-ATLAS challenges that assumption. If it's behaving unusually, if it's carrying unusual chemistry or biology or isotopes, then it's a reminder that the universe is stranger and more dangerous than we often admit. The analogy of a spaceship dumping toxic waste into a river is apt. Even if the amount is small, even if the effects are subtle and delayed, the downstream consequences can accumulate. The solar wind is a river, and 3I-ATLAS is dumping something into it. Whether that something is benign gas and dust or something more exotic, we won't know until we've analysed the data thoroughly. And by then, the object will be long gone, racing back into the dark between stars, leaving us to deal with whatever it left behind. Part 10. The Cosmic Chessboard. Let's pull back and look at the bigger picture. Let's treat 3I-ATLAS not as an isolated curiosity, but as one piece in a grander cosmic game. If intelligent life exists elsewhere in the galaxy, and that's an if the size of the universe itself, then how would such life interact with other star systems? How would they explore? How would they communicate? How would they leave their mark on the cosmos? The Fermi paradox, named after physicist Enrico Fermi, asks a simple question with profound implications. If intelligent life is common in the universe, where is everybody? We've been listening for radio signals for decades. We've scanned the skies for megastructures, Dyson spheres, or other signs of advanced civilizations. We've found nothing. The silence is deafening. So either intelligent life is rare, or it's common but quiet, or it's common but using communication methods we don't recognize, or it existed but went extinct, or it exists but has no interest in us. One hypothesis to resolve the Fermi paradox involves interstellar probes. If you're a civilization capable of interstellar travel, but faster than light travel is impossible, then you send probes. Self-replicating probes, von Neumann machines, that travel to a star system, make copies of themselves using local resources, and send those copies to other star systems. Given enough time, even travelling at sublight speeds, those probes could colonize the entire galaxy. The fact that we haven't detected such probes, or at least we don't think we have, is part of the paradox. But what if we have detected them, and we just didn't recognize them? What if interstellar objects, things like Oumuamua, Borisov and 3I-ATLAS, are not all natural? What if some of them are probes, messenger stones, data storage devices, or fragments of ancient megastructures wandering the galaxy long after their creators are gone? What if 3I-ATLAS is one among many, and our solar system is just one node in a network of systems being monitored, tested, or seeded by civilizations we'll never meet? This is pure speculation, but it's speculation grounded in plausible physics. If you wanted to study a star system, you'd send a probe. If you wanted to influence it, to seed it with life or technology or information, you'd send carriers. Comets are perfect carriers. They're inconspicuous, they're common, and they can travel between stars over millions of years without degrading too much. You could hollow out a comet, fill it with whatever payload you wanted, and send it on a trajectory toward a target star. When it arrives, it heats up, it outgasses, and the payload is delivered. The Sun, and by extension its planets, may have been seeded or tested by other civilizations using interstellar objects as carriers. If that's true, then Earth's life might not be entirely native, panspermia but directed. Or our solar system might have been marked, tagged with some kind of beacon or signal that announces intelligent life here to anyone listening. Or we might be part of an experiment, a long-term study of planetary evolution and the emergence of intelligence. The jet toward the Sun could fit this narrative. If 3I-ATLAS is a probe, and if its mission is to interact with the Sun, then the jet could be an actual tap or test mechanism. Maybe it's feeding data into the Sun's magnetic field, encoding information in solar activity that could be read by anyone watching from a distance. Maybe it's sampling the solar wind, collecting particles to analyse and transmit back to whoever sent it. Maybe it's adjusting the Sun's output, subtly influencing solar cycles to create conditions favourable for life on planets like Earth. These are wild ideas, but they're not forbidden by physics. Let's explore the historical context. Ancient civilizations saw comets as omens, harbingers of change, doom, or divine will. The appearance of a bright comet often coincided with significant events, wars, the deaths of kings, famines. We dismiss this as superstition now, but what if ancient observers were seeing something real? What if some comets were probes, and their appearance was deliberate, timed to coincide with key moments in human history? What if they were observing us, and occasionally intervening, and the legends of comets as omens are garbled memories of those interventions? This is where science and philosophy merge. What tool would an advanced civilization use to influence a star system? They wouldn't invade with spaceships, guns blazing. That's inefficient and unnecessary. They'd use subtle methods, long-term strategies, seed the system with life, wait 1 billion years, see what evolves, adjust solar output slightly, change climate patterns, guide evolution in favourable directions, send probes to monitor progress, collect data, make corrections. By the time intelligent life emerges, the civilization that started the process might be long gone, but their handiwork remains. 3I-ATLAS, in this scenario, is not an accident. It's not a random chunk of ice ejected from another star system by chance. It's a deliberate visitor, part of a network of probes or artifacts that have been visiting star systems for eons. Its odd behaviour, the jet toward the sun, the high carbon dioxide, the large size, these aren't anomalies. They're features. They're signs that it's doing exactly what it was designed to do. If we are the experiment, then what's being tested? Resilience? Intelligence? Our ability to notice anomalies and respond to them? Maybe the test is whether we can recognise 3I-ATLAS for what it is before it leaves. Maybe our response to this object, whether we panic, ignore it, or study it rationally, is being recorded somewhere, added to a database of how emerging civilizations react to the unfamiliar. There's something unsettling about that possibility. The idea that we're being watched, judged, measured against criteria we don't understand. But there's also something oddly comforting. It would mean we're not alone. It would mean the universe has structure, purpose, intention. Even if we're just lab rats in a cosmic experiment, at least we're interesting enough to be worth experimenting on. The cosmic chessboard metaphor is useful here. Think of the galaxy as a board, star systems as squares, and interstellar objects as pieces being moved by players we can't see. Each piece has a purpose, a trajectory, a role to play. 3I-ATLAS is moving toward our sun, and we don't know why. Is it attacking, defending, scouting? Or is it just passing through, a piece that happens to cross our square on its way somewhere else? Without knowing the rules of the game, without seeing the other pieces or understanding the objective, we can only observe and speculate. And here's the kicker. If 3I-ATLAS is part of a network, if it's not alone, then our speculation about what might happen becomes even more urgent. Because if there's one, there might be dozens, hundreds, thousands, all following similar trajectories, all approaching other stars, all doing whatever it is they're designed to do. Some might already have passed through our solar system undetected. Some might be coming in the future. 3I-ATLAS is just the one we happen to notice. So if 3I-ATLAS is not alone, if the sun is part of a network, then the question shifts. It's not just, what will this object do? It's what is the purpose of the network? And more importantly, who built it, and are they still around? Those are questions we can't answer with telescopes and spectroscopy. Those are questions that might require us to fundamentally change how we think about the universe, our place in it, and whether we're ready for what comes next. Part 11. October 2025. JWST's shock black hole. Data. Let's step away from 3I-ATLAS for a moment and look at another cosmic anomaly that emerged in October 2025, because it's relevant to our broader narrative. The James Webb Space Telescope delivered data that sent shockwaves through the astrophysics community. Black holes, those gravitational monsters that form from collapsed stars, were appearing earlier in cosmic history than they should have. Much earlier. The standard model of galaxy formation goes like this. First, you have the Big Bang. The universe expands and cools, hydrogen and helium form. Eventually, gravity pulls that gas together into the first stars, which are massive and short-lived. Those stars burn bright and die young, exploding as supernovae and leaving behind black holes. Over time, those black holes merge, growing larger, and they sit at the centres of forming galaxies, feeding on infalling gas and influencing how the galaxies evolve. The process takes hundreds of millions, even billions of years. But JWST, with its ability to see deep into the early universe, found black holes that were already massive when the universe was only a few 100 million years old. These weren't small stellar mass black holes. These were supermassive, millions or billions of times the mass of our Sun, sitting at the centres of galaxies that barely had time to form. The timeline didn't make sense. There wasn't enough time for stars to form, die, and leave behind black holes that then merged and grew to such enormous sizes. The shock came from realising that our models were wrong. Either black holes can form through pathways we hadn't considered, like direct collapse of gas clouds without going through the star phase, or they grow much faster than we thought, or they were seeded somehow in the early universe, Each explanation requires rethinking fundamental aspects of cosmology and astrophysics, and that's the key point. The universe doesn't care about our models. It does what it does, and sometimes what it does defies our expectations. Why does this matter for 3I-ATLAS? Because it shows that cosmic anomalies, things happening earlier, faster or differently than theory predicts, are not just limited to comets or interstellar objects. They're pervasive. Black holes forming too soon, galaxies assembling too quickly, structures appearing in the cosmic web that shouldn't exist yet. The universe is messier, weirder, more unruly than our elegant equations suggest. The analogy is direct. Just as 3I-ATLAS arrived prematurely or unexpectedly, or behaving in ways that challenge comet physics, black holes appeared prematurely in cosmic history, challenging galaxy formation physics. Both are anomalies. Both force us to ask whether our understanding is incomplete or whether we're witnessing phenomena that require entirely new frameworks. There's a deeper philosophical point here. Science advances by anomalies. When observations don't match predictions, that's when we learn. The Michelson-Morley experiment, which failed to detect the luminiferous ether, led to special relativity. The orbit of Mercury, which didn't quite match Newtonian predictions, led to general relativity. The acceleration of the universe's expansion, discovered in 1998, led to the concept of dark energy. Anomalies are not failures of science, they're opportunities. 3I-ATLAS is an opportunity. Whether it's natural or artificial, whether it's dangerous or benign, it's forcing us to look closely at interstellar objects, at solar dynamics, at the possibility that the universe sends us visitors we don't fully understand. And the black hole data from JWST is a reminder that we should expect the unexpected. The cosmos is under no obligation to conform to our theories. If compressions of stars and galaxies can behave counterintuitively, if the timeline of cosmic evolution is more flexible than we thought, then maybe an interstellar object behaving counterintuitively isn't so surprising. Maybe it's par for the course. Maybe the universe is telling us, through black holes and comets alike, that reality is stranger than our models, and we need to be humble enough to listen. The look-ahead tease is simple. The universe is unruly, and we're going to continue exploring other anomalies that tie into this broader narrative of a cosmos that refuses to follow the rules we've written for it. 3I-ATLAS is one thread in a larger tapestry of weirdness, and pulling on that thread reveals connections to other mysteries, other challenges to our understanding. Part 12. AI predicts stellar collapse events. While we're on the subject of cosmic anomalies and how we try to anticipate them, let's talk about artificial intelligence. In 2025, there have been breakthroughs in using machine learning to forecast stellar events before they occur. Specifically, AI models trained on observational data from supernovae, those massive stellar explosions that mark the death of large stars, have learned to recognize the precursor signatures that indicate a star is about to blow. Supernovae are notoriously difficult to predict. A star can sit quietly for millions of years, then suddenly, over the course of hours or days, collapse and explode. The trigger is often a subtle change in the star's core, where iron accumulates to the point that fusion can no longer support the star against gravity. The core collapses, rebounds, and the outer layers are ejected in a catastrophic explosion. But detecting those subtle precursor changes from light years away is incredibly challenging. Enter AI. Machine learning algorithms, particularly neural networks, are excellent at finding patterns in complex data. Researchers fed these algorithms light curves, spectroscopic data, and other observational signatures from thousands of known supernovae. The AI learned to recognize patterns that humans might miss, subtle variations in brightness, changes in spectral lines, temperature fluctuations that correlated with impending explosions. Now, when telescopes observe a star showing those patterns, the AI can flag it as likely to go supernova soon, giving astronomers advance warning to point more instruments at it and capture the event in unprecedented detail. Why is this important? Because early warning systems are crucial for understanding rare, unpredictable events. Supernovae are scientifically valuable. They produce heavy elements, seed interstellar space with material that forms new stars and planets, and they're one of the ways we measure cosmic distances. Catching a supernova as it happens, rather than after the fact, provides data that improves our models of stellar evolution, nucleosynthesis, and cosmology. But let's connect this to 3I-ATLAS. Could we develop AI models that monitor interstellar objects and predict their interactions with the solar system? In principle, yes. You'd train the AI on data from known comets, asteroids, and interstellar objects. You'd feed it trajectories, spectroscopy, outgassing rates, everything. The AI would learn patterns, correlations between observable properties and subsequent behaviour. Then, when a new object is detected, the AI could predict whether it's likely to fragment, outgas heavily, or behave anomalously. The question is whether AI can handle outliers, events that fall outside the training data. 3I-ATLAS is an outlier. Its chemistry, size, and behaviour don't match the limited sample of interstellar objects we've observed. If the AI was trained on Oumuamua and Borisov, it might not know what to make of 3I-ATLAS. It might flag it as anomalous, which is useful, but it might not be able to predict what it will do next because there's no precedent. This introduces a philosophical tension. We're increasingly relying on machine learning to make sense of complex phenomena, to find signals in noise, to forecast events we can't predict with traditional methods. But AI is only as good as its training data. If the universe throws us a true wildcard, something genuinely unprecedented, the AI might be blind to it. We might miss the warning signs because the algorithm wasn't designed to recognize them. There's also the issue of false confidence. AI models can be overconfident in their predictions, assigning high probabilities to outcomes that turn out to be wrong. If an AI tells us 3I-ATLAS will behave like a normal comet, and we trust that prediction, we might not allocate resources to monitor it as closely as we should. Then, if it does something unexpected, we're caught off guard. Conversely, if the AI flags everything as anomalous, we suffer from alert fatigue, ignoring warnings that might actually be important. The thought here is that 3I-ATLAS may be a wild card, outside trained datasets and models. It's a reminder that no matter how sophisticated our tools, there are limits to prediction. The universe has an infinite capacity to surprise us, and some surprises can't be anticipated by algorithms trained on past events. This doesn't mean we shouldn't use AI. It means we should use it cautiously, with awareness of its limitations, and with human judgment as a critical backup. If we rely too heavily on AI foresight but miss one-off events like 3I-ATLAS, are we still vulnerable? Absolutely. The danger is complacency, the belief that because we have advanced tools we're safe. We're not. We're better prepared than we were, but preparedness has limits. There are scenarios, low probability but high consequence, that we can't fully prepare for. And when those scenarios materialize, our response matters more than our predictions. The connection to 3I-ATLAS is clear. It's an object that defies easy categorization. It challenges models, confounds expectations, and forces us to think critically about what we're seeing rather than relying on automated systems to tell us what to think. Whether it's AI predicting supernovae or astronomers interpreting comet behavior, the principle is the same. Tools are useful, but they're not infallible. Human curiosity, skepticism, and adaptability remain essential. Part 13. Particle Physics. The muon mystery deepens. Now let's shift to something completely different. Or is it? In 2025, the muon magnetic moment anomaly, a puzzle in particle physics, reached new levels of significance. Experiments at Fermilab in the United States measured a property of muons, subatomic particles similar to electrons but heavier, and found that the measured value disagreed with predictions from the standard model of particle physics. The discrepancy is small, but it's statistically significant, and it suggests that there's physics beyond the standard model, forces or particles we haven't discovered yet. For non-experts, here's what this means. Muons are particles that decay quickly, living only about 2 microseconds before transforming into other particles. They have a property called magnetic moment, which describes how they respond to magnetic fields. The standard model, our best theory of fundamental forces and particles, predicts the muon's magnetic moment to extraordinary precision. But experiments keep measuring a value that's slightly off, and the more precise the experiments get, the more persistent the discrepancy becomes. This anomaly suggests that muons are interacting with something the standard model doesn't account for. Maybe there are extra particles, like axions or dark photons, that couple to muons. Maybe there are extra forces, subtle interactions that only become noticeable at extreme precision. Whatever the explanation, it means our foundational understanding of particle physics is incomplete. The rules we thought governed subatomic particles have exceptions or additions we haven't identified. Now, what does this have to do with 3I-ATLAS? At first glance, nothing. Comets and particle physics seem unrelated, but the connection is conceptual. Just as subatomic particles behave unexpectedly, so might macroscopic objects in space. If foundational physics shows surprises on Earth in controlled laboratory experiments, why should we assume space objects will conform to simple expectations? If nature refuses to follow our rules at the smaller scales, maybe it also refuses at the larger scales. Let's speculate wildly for a moment. Could 3I-ATLAS be interacting with unknown forces? The universe is full of phenomena we don't fully understand. Dark matter makes up about 85% of the matter in the universe, but we don't know what it is. Dark energy drives the accelerated expansion of the universe, but we don't know its nature. Magnetic fields permeate galaxies, stars and planets, and they're governed by magnetohydrodynamics, a notoriously complex field. If 3I-ATLAS is travelling through regions of space with unusual dark matter density, could that affect its trajectory or outgassing? If it's interacting with the interplanetary magnetic field in unexpected ways, could that produce the sunward jet? These are purely speculative questions, grounded more in imagination than evidence, but they illustrate a point. When we encounter anomalies, whether in particle physics or comet behaviour, we should be open to the possibility that our understanding is incomplete. The muon mystery also reminds us that science is iterative. The Standard Model was built over decades, combining quantum mechanics and relativity into a coherent framework that explained most observed phenomena. It's been incredibly successful, predicting the existence of particles like the Higgs boson before they were discovered. But it's not the final theory. It has gaps, problems it can't solve, phenomena it can't explain. The muon anomaly is one of those cracks in the foundation, and understanding it will require new ideas, new theories, maybe even a paradigm shift. 3I-ATLAS might be a similar crack in our understanding of comets and interstellar objects. We have good models for how comets behave, based on centuries of observations. But those models are built on solar system comets, objects that formed here and evolved here. Interstellar comets are different. They've seen conditions we haven't, environments our models don't account for. If they behave differently, it's not necessarily because they're artificial or dangerous. It might just be because they're revealing gaps in our knowledge. The philosophical question at the heart of both the muon mystery and the 3I-ATLAS anomaly is this. When nature refuses to follow our rules, what do we do? Do we force nature into our frameworks, tweaking parameters and adding fudge factors until the data fits? Or do we accept that our frameworks are provisional, that reality is messier than theory, and that sometimes we need to rebuild from the ground up? The answer depends on the severity of the discrepancy. Small anomalies can often be accommodated with minor adjustments. Large anomalies require revolutions. We don't yet know which category 3I-ATLAS falls into. Is it a minor curiosity, a footnote in the history of interstellar object studies? Or is it a major anomaly, something that forces us to reconsider fundamental assumptions about comets, the sun, and the risks posed by visitors from beyond? The data is still coming in, the observations are ongoing, and the analysis will take time. But the parallel with particle physics is instructive. Don't assume you understand something just because you have a model. Models are tools, not truth. And when the universe shows you something unexpected, pay attention. Part 14. Earth's magnetic field wobble. Let's come back to Earth for a moment, because while we've been focusing on 3I-ATLAS and the Sun, our own planet has been showing signs of instability. In 2025, there have been increasing reports of anomalies in Earth's geomagnetic field, the magnetic bubble that shields us from solar wind and cosmic radiation. The field isn't static. It fluctuates, it drifts, and over long timescales it even flips, with magnetic north becoming south and vice versa. But recently those fluctuations have been more pronounced, more rapid, and less predictable than usual. The geomagnetic field is generated by the motion of molten iron in Earth's outer core, a process called the geodynamo. As the liquid metal flows, driven by heat from the core and rotation from Earth's spin, it generates electric currents, and those currents produce magnetic fields. The details are complex, involving turbulence, convection, and interactions between the solid inner core and the liquid outer core. Small changes in core dynamics can produce measurable changes in the magnetic field at Earth's surface. What the magnetic field does is crucial for life. It deflects charged particles from the solar wind, preventing them from stripping away our atmosphere. It guides migrating animals, birds, and sea creatures that use magnetic sensing for navigation. It shields us from cosmic rays, high-energy particles from supernovae and other sources that can damage DNA and increase cancer risk. Without the magnetic field, Earth would be a very different, much less hospitable place. In recent years, the field has been weakening in some regions and strengthening in others. The South Atlantic anomaly, a region off the coast of South America where the field is particularly weak, has been growing. Satellites passing through this region experience higher radiation doses and occasional electronic glitches. There's also evidence that the magnetic poles are drifting faster than usual. The North Magnetic Pole, which historically wobbled around northern Canada, has been moving towards Siberia at a rate of about 50 kilometers per year, much faster than the historical average. Some scientists have speculated that we might be approaching a geomagnetic reversal, a flip of the poles. Reversals happen on timescales of hundreds of thousands of years, and the last one occurred about 770,000 years ago. We're overdue in a sense, but overdue in geology means nothing. It could happen tomorrow, or it could happen in 100,000 years. The process itself takes thousands of years, during which the field weakens and becomes chaotic, with multiple poles appearing and disappearing. Now, let's explore the possibility of cosmic factors influencing Earth's magnetic field. Could incoming interstellar objects, unusual solar interactions, or other external forces subtly affect the geomagnetic field? Mainstream geophysics attributes most changes to internal Earth processes, the dynamics of the core, mantle convection, and so on. But there are suggestions, speculative and controversial, that external triggers might play a role. For example, some researchers have proposed that impacts from large asteroids or comets could disturb the core mantle boundary, potentially influencing core dynamics and the geodynamo. Others have suggested that variations in cosmic ray flux, which are influenced by solar activity and the Sun's magnetic field, could affect cloud formation and climate, which in turn could influence ocean currents and atmospheric circulation, which might feed back into the geomagnetic field through complex coupling mechanisms. These ideas are fringe, not widely accepted, but they illustrate that the Earth system is interconnected in ways we don't fully understand. Could 3I-ATLAS, by adding dust, charged particles, or sublimated material to the inner solar system, influence Earth's magnetosphere? The magnetosphere is the region around Earth shaped by our magnetic field, and it interacts with the solar wind. If 3I-ATLAS's outgassing changes the density or composition of the solar wind, even slightly, that could affect how the magnetosphere responds. More particles mean more pressure on the magnetosphere, compressing it, potentially allowing more cosmic rays to penetrate. There's also the possibility of a cascading effect. Sun interacts with comet, producing enhanced solar wind or a coronal mass ejection. That CME hits Earth, compressing the magnetosphere, inducing currents in the ionosphere and upper atmosphere. Those currents couple to lower atmospheric layers, affecting weather patterns. Changes in weather affect ocean currents. Changes in ocean currents, over long time scales, could influence heat distribution in the mantle, which might affect core dynamics. It's a long chain of causality, each link tenuous, but not impossible. Let's be clear. The mainstream scientific view is that Earth's magnetic field changes are driven by internal processes, and external factors like solar wind variations or cosmic ray flux are minor contributors at best. But we're exploring what-ifs here, pushing boundaries, asking whether the arrival of an anomalous interstellar object could have subtle, indirect effects on our planet beyond the obvious ones. The transition to the next part is natural. We've looked at external cosmic threats, black holes forming too soon, muons behaving oddly, and internal Earth vulnerabilities, the magnetic field wobbling. Now we bring it all together, synthesizing these threads into a coherent picture of where we stand. Humanity at the edge, facing a universe that's more complex, more unpredictable, and potentially more dangerous than we've been comfortable admitting. Part 15, the final synthesis. Humanity at the edge. Let's recap the journey we've taken. We started with an image of 3I-ATLAS showing a jet of gas directed toward the Sun, defying every expectation of how comets should behave. We explored the object's physical and chemical makeup, its high carbon dioxide content, its water emissions at impossible distances, its large size and hyperbolic trajectory. We dove into speculative possibilities, artificial probes, alien megastructures, sun mining or sun-triggering mechanisms. We examined the vulnerabilities of the Sun and Earth, coronal mass ejections, geomagnetic storms, the fragility of our technological civilization. We counted down to perihelion, understanding that late October 2025 marks the closest approach, the moment of truth. We traced the history of interstellar visitors, Oumuamua, Borisov, and now 3I-ATLAS, each stranger than the last. We explored exotic scenarios, comets aiming at stars, jets powered by magnetic reconnection or intentional engineering. We asked whether military and intelligence agencies are hiding what they know, whether solar observatories have gone dark, whether there's information being withheld for reasons of national security or operational capability. We ventured into biological and energetic nightmares, panspermia carrying alien microbes, exotic isotopes releasing radiation, subtle effects on climate and mutation rates. We placed 3I-ATLAS on the cosmic chessboard, considering whether it's part of a network of probes or artifacts, whether the Sun and Earth are being monitored, tested, or influenced by intelligences we can't comprehend. Then we broadened the view, connecting 3I-ATLAS to other anomalies in 2025. Black holes forming earlier than they should, challenging cosmological models. AI systems learning to predict supernovae but potentially blind to unprecedented events. The muon magnetic moment anomaly, revealing cracks in the standard model of particle physics. Earth's magnetic field wobbling, possibly influenced by cosmic factors we haven't fully considered. The core takeaway is this. We are entering an era where anomalies are not outliers. They might be signals. The universe is sending us messages through black holes and muons and comets and magnetic fields, and the message is that our understanding is incomplete. We live in a cosmos that's stranger, more dynamic, and less predictable than our textbooks suggest. And when an interstellar object like 3I-ATLAS arrives, behaving in ways we didn't anticipate, it's a test. Not necessarily imposed by aliens or gods, but a test nonetheless. A test of our ability to observe, to analyse, to remain rational in the face of the unknown. Let's restate the worst-case scenarios, because they're important even if they're unlikely. First, the object triggers a solar storm. Through outgassing, particle injection, or magnetic disturbances, 3I-ATLAS contributes to a coronal mass ejection that hits Earth. Power grids fail, satellites are damaged, GPS goes down, communication networks falter, planes are grounded, supply chains break, and for days or weeks modern life grinds to a halt. It's not civilization ending, but it's civilization disrupting, and in a world as interconnected as ours, disruption cascades into crisis. Second, the object carries exotic biology or radiation. Microbes from another star system, hardy enough to survive interstellar travel, are released into the inner solar system. Some reach Earth, surviving atmospheric entry, and introduce alien biochemistry into our biosphere. Or radioactive isotopes, rare and dangerous, contaminate satellites and space stations, increasing radiation doses for astronauts and potentially affecting high-altitude aircraft. Again, not apocalyptic, but unsettling and unpredictable. Third, the object is artificial, or partially artificial. A probe, a fragment of a megastructure, a data storage device, something built by an intelligence that's not human. Its proximity to the Sun is intentional, part of a mission or experiment we don't understand. When it reaches perihelion, it does something. Sends a signal, collects data, triggers an event, or simply observes and records. The implications are enormous, not just scientifically, but philosophically, politically, socially. If we're not alone, if something out there is watching, studying, or interacting with us, then every assumption we've made about our place in the universe needs revision. Now let's balance that with reassurance. Scientists currently assess no immediate threat to Earth from 3I-ATLAS. The object's trajectory doesn't intersect our orbit. Its distance at closest approach is safe. The probability of it causing a significant solar event is extremely low. The likelihood of it carrying viable alien life is vanishingly small. The chance that it's artificial, while non-zero, is not supported by any concrete evidence. Most likely 3I-ATLAS is a natural comet, weird but not dangerous, interesting but not threatening. But here's the provocative question. If we witness nothing dramatic, what will we learn? We'll learn that interstellar objects can have unusual chemistry, that carbon dioxide-dominated comets exist, that outgassing can occur far from the sun, and that our models need updating. We'll learn humility, that the universe doesn't owe us predictability. And we'll learn preparedness, that even when nothing bad happens, the exercise of considering worst cases helps us build resilience. And if we witness something unusual, if 3I-ATLAS does trigger a solar event, or fragment spectacularly, or reveal structure inconsistent with natural formation, then we learn even more. We learn that our solar system is not isolated, that visitors from beyond can have effects we didn't anticipate, and that monitoring, studying and responding to such visitors is not just academic curiosity but practical necessity. There's an action point here, a perspective shift. We should follow upcoming observations. Perihelion is imminent. The data will be flowing in from JWST, Hubble, ground-based observatories. Spectroscopy will reveal chemical changes, imaging will show structural evolution, trajectory measurements will detect any deviations. The scientific community will publish analyses, debates will occur, and over time we'll build a clearer picture of what 3I-ATLAS is and what it's doing. But beyond the data, there's a broader reflection. How ready are we for cosmic surprises? Not just comets, but supernovae, gamma-ray bursts, asteroid impacts, solar flares, any of the myriad ways the universe can intrude on our carefully constructed sense of safety. We're more capable than ever, with technology, knowledge and global cooperation. But we're also more vulnerable, dependent on fragile systems that can fail catastrophically. The balance between capability and vulnerability defines our era. Let me close with a microstory, a metaphor. Imagine a lone messenger, speeding toward the sun. It's been travelling for eons through the dark between stars, carrying something, maybe just ice and rock, maybe information, maybe a purpose. It doesn't know we're watching. It doesn't care. It's just doing what it was set in motion to do, whether by gravity or design. And we're in the audience, humans on a small blue planet looking up, trying to understand. Whether 3I-ATLAS whispers, explodes or disappears unharmed, the fact we're watching matters. It means we're paying attention, we're asking questions, we're not content to accept the universe at face value. That curiosity, that willingness to stare into the unknown and demand answers, is what makes us human. It's what drives science, art, exploration, progress. And it's what will carry us forward, whether the universe decides to follow our rulebook or tear it up and show us something entirely new. The question isn't only what 3I-ATLAS will do. The question is how we respond if the universe decides not to follow our rulebook. Do we panic? Do we adapt? Do we learn? The answer to that question will define not just this moment but every moment that follows, as we continue to encounter the strange, the unexpected and the wondrous in the cosmos we call home.